Welcome to episode 1 of our Azure Kubernetes Service Networking Masterclass. Today we begin with the most important lesson in Kubernetes networking. Before you learn Ingress, Application Gateway, NAT Gateway, Cilium, or load balancers, you must first understand how a packet moves through a Kubernetes cluster. Most engineers learn Kubernetes networking backwards. They start with an ingress controller because they need to expose an application. They deploy a load balancer because a tutorial tells them to. They configure networking policies because a security team requests it. But they never understand why these technologies exist in the first place. In this episode, we are going to fix that. Imagine we are building a modern digital banking platform. Customers access mobile banking, internet banking, payment services, loan applications, fraud detection systems, and customer service applications. Rather than deploying hundreds of virtual machines, we decide to use Azure Kubernetes Service, commonly called AKS. The business objective sounds simple. Deploy applications quickly. Scale automatically. Remain highly available. Remain secure. But the moment we deploy our first container, a networking problem appears. How does everything communicate? How does one application find another? How does security get enforced? How do thousands of containers share a network without creating chaos? Those questions are exactly why Kubernetes networking exists. Let's start from the beginning. When people come from traditional infrastructure backgrounds, they think in terms of servers. Server A talks to server B. Server B talks to server C. Each server has its own IP address. Those servers typically exist for months or years. Kubernetes changes everything. Containers are constantly created and destroyed. Pods appear and disappear. Applications scale up and down throughout the day. The networking model must accommodate change as a normal operating condition. Kubernetes solves this challenge using 3 fundamental rules. Rule number 1. Every pod gets an IP address. Rule number 2. Pods can communicate with each other without network address translation. Rule number 3. Applications should not care which pod is running because services provide stable access points. These 3 principles sound simple, but they form the foundation of everything we'll discuss throughout this podcast series. Let's visualize the architecture. Suppose our banking platform contains a customer service application, a payment service, an authentication service, a fraud detection service, and a customer database. Each application is running inside one or more pods. The payment service doesn't need to know which specific authentication pod exists at any moment. Instead, it communicates through a Kubernetes service. The service provides a stable name. The service provides a stable virtual IP. Pods behind that service can change continuously. From the application's perspective, nothing changes. This abstraction is one of Kubernetes' greatest strengths. Now let's discuss where Azure enters the picture. Azure Kubernetes Service runs Kubernetes on top of Azure networking infrastructure. Behind the scenes, AKS integrates with Azure Virtual Networks, Azure Subnets, Azure Routing, Azure Load Balancing, Azure Security Controls, and Azure DNS Services. Think of Kubernetes as the operating system. Think of Azure networking as the underlying road network that enables everything to move. Every AKS cluster must exist inside a networking environment. That environment begins with an Azure Virtual Network, often called a VNet. A VNet is essentially a private network in Azure. Within that VNet, we create subnets. AKS nodes live inside those subnets. Those nodes host Kubernetes pods. If you understand VNets and subnets, you already understand a significant portion of AKS networking architecture. Now let's talk about one of the most important decisions an AKS architect makes: choosing the networking model. Microsoft provides two primary networking approaches: overlay networking and flat networking. Let's begin with overlay networking because it has become the preferred architecture for most deployments. In overlay networking, pod IP addresses come from a separate address range that is distinct from the node subnet. This means pods receive addresses from a dedicated Kubernetes address space. The node subnet remains separate. Why is this important? Because IP addresses are one of the most precious resources in enterprise networking. Large organizations often struggle to obtain enough address space. Imagine a banking organization deploying hundreds of clusters across multiple regions. Each cluster may host thousands of pods. Without careful planning, IP exhaustion becomes a serious problem. Overlay networking dramatically reduces IP consumption. The Azure Virtual Network only needs enough addresses for nodes. Pod addresses exist within a separate logical range. This approach improves scale and simplifies management. For many organizations, Azure CNI Overlay is becoming the default choice because it conserves scarce IP space while supporting large-scale container deployments. Now let's compare that with flat networking. In flat networking, pods receive IP addresses directly from the Azure Virtual Network. Every pod becomes a first-class citizen in the VNet. External systems can communicate directly with pod IP addresses. Some organizations require this approach. For example, certain security appliances, legacy applications, monitoring systems, or network visibility tools may expect direct visibility into pod identities. The advantage is direct connectivity. The disadvantage is IP consumption. Very large environments often discover they need significantly larger address spaces. This is why architecture decisions made today can affect operations years into the future. Choosing the wrong network model can become extremely expensive to reverse later. Now let's introduce a term you'll hear frequently throughout your Kubernetes journey: CNI. Container Networking Interface. The simplest way to understand CNI is this: Kubernetes knows how to schedule workloads. CNI knows how to connect workloads. The CNI plugin determines how pod IP addresses are assigned. It determines how routing works. It determines how packets move between workloads. It determines how services are reached. In AKS, Azure provides multiple CNI options. Each option exists to solve specific architectural requirements. This is where many engineers become confused. They assume CNI is simply a networking driver. In reality, the CNI decision influences scalability, performance, security, operations, troubleshooting, and cost. Let's dive deeper into Azure CNI. Azure CNI was designed to integrate Kubernetes networking with Azure networking. Unlike traditional Kubernetes deployments that completely isolate pod networking, Azure CNI creates a much tighter relationship between pods and Azure networking services. Why does this matter? Because enterprise organizations want security teams, networking teams, and platform teams to work together using familiar tools. Azure CNI enables that alignment. Now let's discuss one of the least understood topics in AKS: IPAM. IP address management. Every pod requires an IP address. AKS must allocate those addresses efficiently. If you fail to design IP planning correctly, your cluster can experience scaling failures even when CPU and memory resources remain available. Imagine our banking platform launches a new marketing campaign. Suddenly customer traffic increases dramatically. Kubernetes attempts to scale from 100 pods to 1,000 pods. Everything appears healthy. CPU is available. Memory is available. Storage is available, but no new pods can start. Why? Because the subnet has no available addresses. This is one of the most common production networking failures. Effective IPAM begins during architecture planning, not after deployment. Whenever you design AKS, always estimate future growth, not current growth. Future growth. Many architects size networks for today's workloads. Great architects size networks for tomorrow's workloads. Now let's discuss data plane architecture. Control plane and data plane are often confused. The control plane makes decisions. The data plane moves packets. The control plane decides where traffic should go. The data plane actually delivers the traffic. Imagine airport operations. Air traffic controllers make decisions. Aircraft move passengers. The controllers represent the control plane. The aircraft represent the data plane. In Kubernetes networking, the data plane determines how efficiently packets are forwarded between workloads. And this leads us to one of the most transformative technologies in modern cloud networking. Cilium. To understand why Cilium matters, we must first understand a traditional networking challenge. Historically, packet filtering relied heavily on technologies such as iptables. As environments became larger, rule management became increasingly difficult. More rules resulted in greater complexity. More complexity resulted in more overhead. Cilium introduced a different approach. It leverages a Linux technology called eBPF. Think of eBPF as programmable networking intelligence operating directly inside the Linux kernel. Rather than sending packets through layers of processing, eBPF allows traffic decisions to occur much closer to where packets are handled. The result can be improved scalability, improved observability, simplified policy enforcement, and lower operational complexity. This is why Cilium has gained enormous momentum across the Kubernetes industry. When Microsoft introduced Azure CNI powered by Cilium, it represented far more than a feature update. It represented a shift toward the future of Kubernetes networking. Now let's discuss observability. One of the hardest parts of networking is understanding what actually happened. When an application fails, developers often hear the dreaded statement, "It's a network issue." But nobody knows what that means. Cilium introduces advanced visibility capabilities. You can observe traffic flows. You can understand service communication paths. You can identify policy violations. You can troubleshoot connectivity problems much faster than traditional approaches. For large organizations running mission-critical platforms, observability is becoming just as important as connectivity itself. Now let's examine another important question. Can I bring my own CNI? The answer is yes. Some organizations choose alternative networking solutions. There may be regulatory requirements. There may be existing operational expertise. There may be advanced networking capabilities unavailable elsewhere. However, there's an important lesson here. Every customization increases ownership responsibility. The more you deviate from platform defaults, the more operational complexity you inherit. This is why the best architecture is rarely the most customized architecture. The best architecture is often the simplest architecture that satisfies business requirements. Now let's turn our attention to security. Security is one of the primary reasons networking design matters. In traditional environments, organizations often focused heavily on perimeter security. Protect the edge. Protect the firewall. Protect the gateway. Modern cloud-native environments require a different mindset. Assume compromise. Limit blast radius. Apply least privilege access. Restrict unnecessary communication. This philosophy leads us to network policies. Network policies determine which workloads can communicate, with which other workloads. Imagine our banking platform. Should the marketing application communicate directly with the payment processing service? Probably not. Should the fraud detection service access every workload? Again, probably not. Network policies provide precise control over communication patterns. Instead of allowing unrestricted connectivity, we explicitly define trusted relationships. This creates segmentation. Segmentation limits risk. Risk reduction improves security. Security improves resilience. Historically, many AKS environments used Network Policy Manager, commonly called NPM. As Kubernetes networking evolved, organizations increasingly migrated toward Cilium-based network policies. The reason is straightforward. Cilium provides a modern policy engine built on eBPF technology. It often delivers better scalability, improved observability, and stronger long-term strategic alignment. However, migrations require careful planning. Never assume policy migration is simply replacing one tool with another. Policies should be reviewed. Traffic flows should be understood. Dependencies should be documented. Testing should occur before production cutovers. One of the best practices I have seen across enterprise environments is this. Document communication patterns before enforcing restrictions. Many teams create policies before understanding application behavior. That approach often breaks production systems. Observe first. Document second. Enforce third. Now let's bring together everything we've discussed. Our digital banking platform now has an Azure Virtual Network. It has subnets. It has AKS nodes. It has pods. It has services. It has a networking model. It has Azure CNI. It has IP management. It has network security policies. It has observability. It has a modern Cilium-based architecture. The applications can communicate. Security boundaries exist. Network governance exists. Platform teams can scale confidently. But we still have a major problem. Customers cannot access the application. The platform is running. The services are healthy. Yet internet users have no way to reach them. The next question becomes incredibly important. How does external traffic enter the cluster? How do we expose applications securely? How do DNS, SSL certificates, load balancers, application gateway, custom domains, and Nginx fit into the architecture? Those questions take us directly into episode 2. In the next episode, we'll follow a customer request from a browser all the way into a pod running inside Azure Kubernetes service, and along the way, we'll unravel ingress, application gateway, application routing, custom domains, SSL, private DNS, Nginx controllers, and every major ingress architecture pattern used in production AKS environments today. Until then, remember this. Great Kubernetes architects don't start with load balancers. They start with packet flow. Because once you understand how packets move, every networking decision becomes easier to understand. And that is the foundation upon which every successful AKS platform is built.